let's learn convolution theorem. Yeah. The property. So the last time we talked about properties, linearity property, derivatives. Yeah. Here it's another one, convolution theorem. Yeah. In Laplace transform, we learned convolution theorem. That's the Laplace transform version. So here we have a similar version, the Fourier transform version. Yeah. All right. First, so let's look at the review the convolution operation. Yeah. The definition of convolution. Yeah. So the convolution operation is defined in this way. We apply the convolution operation on two given functions, f and g, f function and a g function. Then we use another function, h function, to denote the convolution of these two functions. The convolution definition is the integral of this form. Integral. Yeah. Yeah. Here you can see this version definition slightly different from Laplace transform definition. Yeah. At that time, because the integral limit for our Fourier transform, the lower limit is negative infinity. Yeah. Yeah. So for the Fourier transform, lower limit is the 0. Yeah. So that's the, one important difference. Yeah. Other than that, so then another version. So here, this version, these two versions equivalent. Just we do some variable substitution. So we can change from one version to another version. Yeah. So with this convolution definition, then we apply Fourier transform on the convolution of two functions. And let's see what would happen. Yeah. All right. So let's recall the Laplace transform of convolution. Yeah. All right. Laplace transform. Yeah. Now you can see. At that time, when we define convolution of two functions, f function, g function, you can see, the similar format, but here you can see, lower limit, upper limit, it's different. Yeah. Yeah. So here you can see, our definition slightly different. Yeah. All right. So then, when we apply Laplace transform on this convolution operation, we get the other side, the product of Laplace transform of those two functions, f, g functions. Yeah. So very nice operation. Yeah. Yeah. So the transform side, just a direct product. Yeah. All right. Now let us go to the Fourier transform case. Yeah. The similar property. Yeah, because here you can see the definition of Laplace transform, Fourier transform. If you consider structure, pretty similar. The integral, right? Yeah. So we call it integral transform. So they're both integral transform. But the way to define the integral transform slightly different. Yeah. Then, if we do the convolution, so you can see, the property should be similar. Yeah. So let's look at the convolution theorem. Yeah. Suppose that f function, g function are piecewise continuous. Yeah. Piecewise continuous. Yeah, here. Yeah. Bounded. Yeah. So also bounded. Yeah. Josh, just join us. All right. Bounded. Yeah. All right. And they're absolutely integrable on the x-axis. Yeah. All these conditions listed here, just want to make sure the Fourier transform is well defined. Yeah. Well defined. The definition, the Fourier transform, well defined. Yeah. Absolute integrable. Yeah. If it's absolute integrable, yeah. So then if you look at the integral of the Fourier transform, you take absolute value, convergent, yeah, not divergent. Yeah. Yeah. All right. So then under these conditions, then we can apply Fourier transform. Yeah. Yeah. Then the result, the Fourier transform of the convolution left-hand side. Right-hand side, the product, yeah, but here you can see there is a constant. Yeah. Yeah. There is a constant. Yeah. The constant, the thing about the constant, because it relates to the definition of the Fourier transform. Yeah. So here, yeah, based on the definition, yeah, so we, there is a constant, so we have to, keep that constant. Yeah. So that's something a little different from the Laplace version. Laplace version, no, constant 1. Yeah. So it looks perfect. Yeah. So here there is the constant is not 1. Yeah. People feel just not that perfect. Yeah. Not that perfect. Yeah. Yeah. But it's okay. Yeah. So in our real world application, we just, yeah, do a little more. Yeah. All right. Yeah. So that's the Laplace transform. Sorry, that's the convolution operation. Yeah. In this yesterday, I opposed the assignment part 4B. Yeah. Homework assignment 4, part B. Yeah. Yeah. In that assignment, I didn't give you the convolution questions. Yeah. So I try to cover all the topics. Yeah. In module 5. Yeah. But this convolution topic still, I couldn't find an interesting question, so I didn't give you that question. Yeah. So later, if I can find an interesting question about the convolution, so I may talk about it in our review session. Yeah. So next week we will do review session. Yeah. So this week we try to complete module 5. Yeah. The next week we will have 2 classes, so I can do the review for the final. Yeah. All right. Next. Yeah. Yeah. This is another representation. Yeah. 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 So here, yeah. Because, yeah. So here we can do the inverse Fourier transform. How to see that? Yeah. Because from this formula, let us do inverse Fourier transform. Let's apply inverse Fourier transform. Yeah, inverse Fourier transform. Then inverse to this side, right? Yeah. And capital F, this notation, we use that little hat notation. Yeah, little hat notation. Then the definition of inverse Fourier transform, this integral, then consider the constant. There is a cancellation, right? Here we need to multiply this constant, but inverse transform we have 1 over root of 2 pi. So cancel out. Yeah. So here you can see the inverse Fourier transform. yeah, the leading constant becomes 1. Yeah, becomes 1. Yeah, yeah. So divergence. So here you can, yeah, yeah, yeah. Right. So this, I try to find a chance to practice this property. Yeah, because the convolution, this property, is important for the Fourier transform. Yeah. So in the review session, if I can find an interesting question, so then I will give you one example. Yeah. So then in the final, so we can practice one similar example. Yeah. All right. But if I cannot find an interesting example, then we just forget about it. Yeah. All right. Yeah. Then the next we move to, before we move to the next topic. Yeah. So next, because there is an important topic next, so I want to say something about the Fourier. This is the definition of the Fourier transform. Yeah. So I show you this original definition here. Yeah. All right. So this question, this definition, yeah, we work on a function. What is this f function? Right? If we look at this function is a piecewise continuous, bounded, yeah, absolutely integrable, yeah, that kind of function. Yeah, nice function. So, you know, good enough. So we say this function should be good enough. So then we can take the Fourier transform. Yeah. Then another question. Yeah. Why we do Fourier transform? Right? Yeah. So we go back to, you know, previous lecture. Yeah. Why we apply Fourier transform on a given function. Yeah. The answer is simple, like this. Yeah. We change the domain, right? Yeah. When we apply the Fourier transform, we move from time domain to the frequency domain. Yeah. So here, after the Fourier transform, this W you see here. So now the function. Yeah. So here we original function, f function. Now the transform function. Yeah. Original function. Yeah. Here we can assume it's in the time domain. Yeah. Or could be in the spatial domain. Okay. Yeah. Time domain or spatial domain. Yeah. Yeah. So here, yeah. Let's just, for simplicity, let's say time domain. Then this side, yeah, yeah, the transform, you know, different domain, completely different domain. So the domain here we call frequency domain. Here we use this frequency concept. Frequency, high frequency, low frequency. Okay, yeah. So the music, you know, the wave, the curve, high frequency, low frequency, right? Yeah. So here, if I draw a simple diagram to show you the shape, I use the wave shape to show you high frequency, low frequency curve. Yeah, you can get an idea. Okay? All right. First, let me draw curve with, you know, relatively high frequency. Okay? Yeah. You can see at a, you know, fixed period of time, you know, the periods, well, there are more periods in the fixed interval of the time. Then low frequency. Let me draw another curve with low frequency. See, that's low frequency. Okay, yeah. So the, you know, period longer. Yeah. Here you can see the frequency and the period. Frequency and the period has a very close relationship. Yeah. The relationship is like the longer the period, the smaller the the smaller. Yeah, smaller means lower, right? Yeah. So this higher frequency, okay? This higher frequency, this lower. Yeah, lower frequency. All right, yeah. So here you can see when we define frequency, actually we did once before, right? Yeah. When we in our module 2, we used this concept, module 2. Yeah. Remember when we talk about that resonance concept, the frequency. Yeah. We define that. The definition is the frequency F equals reciprocal of the period. Okay, period. Yeah. Or we call it fundamental period. Yeah. Because period, if it's not fundamental, then any integer multiple, positive integer multiple of the fundamental period, we can all call period. Yeah. So F is just a reciprocal of the period. Yeah. Here you can see, yeah, reciprocal. Yeah. All right. Yeah. Here, after we review this frequency concept, now you can see the Fourier transform represents the original function in the frequency domain. Yeah, in the frequency domain. Yeah. 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 So you can see we use a completely different representation to represent the original function. Yeah. Because then the benefit is obvious. Yeah. Because when you do this, people may ask, what's the benefit? Right? What's the benefit? The benefit is in a different domain, or just like in a different world, okay? Different universe. Yeah. So you jump to different universe. Okay? Then what you can see, what you can do, completely different. What you can see or what you can do, quite different. Yeah, because in the old universe, a lot of things hidden, you cannot see, right? Yeah, but now you jump to a completely different universe. Then a lot of hidden things you can see. Okay? Then you can do much more than before. All right? Yeah. I will give you an example. Yeah, simple example to let you understand. Yeah, because this background is important. Yeah. 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 So because for the engineering class, we need a lot of background. Yeah. So if we only study the math formulas, that's not enough. Yeah. We need to know how to, in the real world situation, how do we apply these formulas? What's the meaning? Yeah, the background. Yeah, so here we want to connect. Yeah. The Fourier transform, very useful in the real world applications, engineering problems. Yeah. But how to connect, right? How to. Yeah. So why the Fourier transform is closely related to, real world phenomena, right? Yeah. So here I want to give you some concrete example. Yeah, here. Yeah. All right. So here. Yeah. So let me move to next slide. Let me give you a little more background related to the frequency. When you jump to the frequency universe, what you can see, in the old universe, something hidden you can see in the new universe. That's the point. Yeah. In the old universe, time domain, frequency, spatial domain, yeah, because a lot of properties are hidden. Hard to see, or how to separate. You can see, but messed, you know. Yeah. So let me use a little space here. Let me describe a basic, important application problem in the real world. Yeah. The denoising application. Let us look at the denoising. Yeah. So it's a, you know, very basic, very useful application in our daily life. Yeah. So that's the denoising. Application. Okay, let's look at that. Okay, denoising application, very useful. Yeah. So here you can talk about in a sound file or in an image file or video file, there is some noise there. Okay, yeah, noise there. All right, yeah, you can see the noise. Yeah, so, yeah, and you want to find a way, find some algorithm, yeah, you know, some software algorithm to remove or greatly remove. May not be 100%, right? It's hard to remove the noise 100%. Probably 90-something% you want to remove the noise. Yeah, that kind of application. But the question, when you remove the noise from the original file, it's not easy, because the noise part mixing with the good signal part. Yeah. How do you separate? Okay, hard to separate. So the difficulty is hard to separate the noise from the signals. Or, you know, good signals. Okay, yeah, because noise we can treat as signals. Yeah, yeah, but bad signals. Yeah, all right. Yeah, yeah. That's the old universe, because something hard to do. Yeah, yeah. Now, after people discovered Fourier transform tool, this powerful mathematical tool was created. Then, so people apply the Fourier transform. On the signal function. Okay, signal. You have a function, signal function. Yeah, the signal function. Yeah, I will elaborate it. Yeah, in our next topic, D.2, we will talk about that signal function. Okay, now we apply the Fourier transform on our signal function. Okay, yeah. What do we get? Okay, yeah. So we get a transform result. That transform result is another function in the frequency domain. Okay, yeah. So we get a new function in the frequency domain. Okay, yeah. All the function, if we use f of x, okay, new function we use f hat of w. Okay, yeah, a new representation. But in this, yeah, so if we call it, now we jump to a new universe. Then we can see the content of our signal. Yeah, so we have the content, right? Yeah. So the content of the signal was buried in that original function, but when we do the transform, this new function also contains all the content, right? Yeah. No different. Yeah. There is no loss in the content when we do the Fourier transform. No loss. Why? Because when we do the inverse Fourier transform, we can completely recover to the old signal, right? Of inverse Fourier transform. Yeah. So if we apply inverse Fourier transform on this frequency representation of the original function, we go back to the original function. No loss, okay? That's why our understanding. So when we do the Fourier transform, the content of the signal, no loss. Yeah, it's all here. Yeah, but because the representation is different in this new frequency domain, then if we want to draw the curve of the function, yeah, you can draw the curve of the function. Okay, yeah. When you draw, some part low frequency, some part high frequency. Okay, yeah, because now we look at the function, in the frequency domain, low frequency, high frequency. Then people observed there is an important property in this frequency domain. So people want to take advantage of this property. Okay, so what's that property? New property. The new property is the noise part appears in the high frequency part. High frequency part, not low frequency part. Yeah. Noise part. Yeah. Yeah. Appears. Yeah. Yeah. Located. Yeah. Or yeah. Yeah. It's better. Yeah. So we can say yeah, is located. In the high frequency part. Yeah. All right? Because high frequency and the low frequency can be separated relatively easier. Yeah? You have high frequency, low frequency, yeah. Could be separated relatively easier in the frequency domain. Okay? Yeah. Higher frequency, yeah. Because this curve here I show you, low frequency, high frequency, this shape is pretty much in the time domain, okay? Yeah, because this understanding in the time domain. But in the frequency domain, high frequency appears, the value, because this is a frequency axis, okay? Yeah, the frequency value, yeah, low frequency here, high frequency there, higher. Okay, low frequency lower. All right. But the noise, most of the noise located in the high frequency part. How to remove the noise? Cut off the high frequency. Okay, yeah, you cut off. Yeah. Then most of the noise removed. Yeah. But when you cut off the high frequency part, you may cut off the good signal part, a little bit, yes, that's true. Yeah, because when you cut off, high frequency part also contains part of the good signal content. Yeah. So when you cut off, you drop, you have some loss in the good signal. Yeah. But the noise is reduced significantly. Yeah. The good signal part, there is a small loss, but it's not a big loss, small loss. Yeah. So you can take it. Yeah. So you feel much better. Yeah. After we do this kind of more noise removal technique, then we need to go back to by the Fourier inverse transform, we need to go back to the time domain. Yeah. Finally, at the end, you need to go back to the time domain after cut off the noise high frequency part. Yeah. Then the signal you recovered, the noise reduced significantly, with slightly good signal loss. Okay, some minor loss. Yeah, but you can accept the processing result. Yeah, so that idea. Okay, yeah. So here I use this example, denoising example, to explain why the Fourier transform is so useful in the real world applications. Give you some idea. Yeah. You work in the frequency domain. Okay. Yeah. Things quite different. Yeah. Yeah. Here just example, because then many other applications people can do a lot of different ways the processing. Yeah. Yeah. Basic, but the high level idea pretty much like this example. Yeah. Like this example. Okay? Yeah. All right. But the next, now we need to move to our D.2 topic, discrete Fourier transform. Yeah. Here you can see this keyword, discrete. Yeah. That means our previous version we learned, it's a continuous version Fourier transform. Yeah. So here we need to change from continuous version to discrete version. That change. Continuous version to discrete version. That change. Yeah. But you may like to ask why. Right? Yeah. The continuous version, quite nice, right? Yeah. We have so many nice properties for the continuous version. Why you need to consider a discrete version of the Fourier transform? Yeah. The answer is very simple. The answer, because the reason we apply Fourier transform, we want to solve the real world problems, but what's the data we need to process in the real world, right? We need to look at the data we have in the real world. Yeah. So, real world data format. What kind of format do we have? Yeah. Look at the data. Okay. So what's the data here? For example, sound file, it's data, right? Yeah. So when you get a sound file, sound file, it's your data. Yeah. Then image file. When you get an image file, it's your data. And a video file, it's your data, right? Yeah. And other data, a lot of other stock data. Stock, it's data, right? Yeah, you know, stock data. Yeah. A lot of other data, satellite data, okay? Yeah. The data in the real world, yeah. Then, if you examine the data, what's the format of the data in those examples? What's the format? Okay? Yeah. You can see the most, here we cannot say 100%. Yeah. Yeah. Most of them, the data we collect from real digital data, right? Digital data. Yeah. Data in numbers, right? Yeah. So your sum file, you know, numbers. You use, you know, a sequence of numbers to represent the content of your sum file. Okay? Image, you use numbers to represent the grayscales, right? Yeah. You know, image, the pixels. Yeah. The, you know, RGB values, right? RGB values, all numbers. Yeah. So what do you get? The data in the real world, the format of the data. Typically, yeah, but not 100%. No. Here, I do not want to say 100% because there are different cases. Yeah. All right, so most of them are digital data. Digital data, digital signals. Yeah. Digital, so the format, yes, here, the format is a sequence of numbers. So the data, the form of the data, it's a sequence of numbers. That's the format. Yeah. That means when you represent a function, you do not have a continuous function. Yeah? You do not have a definition of the continuous function. You have a sequence of numbers to represent a function. That sequence of numbers we can only call the discrete version of a function. It's not a continuous version of a function. So the data we collected from the real world, typically we need to use a discrete function to represent it, not continuous function. Okay? Yeah. We do not have sine, cosine, continuous function representation. We don't have. Yeah. We have a sequence of numbers as our data. Okay? That's why how to process discrete form of the data. So we need to modify our Fourier transform from continuous version to discrete version. That's the reason we need to study the discrete Fourier transform. Okay? Yeah. All right. So with this background, now let's move to this topic, discrete Fourier transform. Let's see how to modify the Fourier transform definition. Yeah. From analog to discrete. Analog, yeah. So the continuous version of the signal, analog signal. Okay? Yeah. Then we need to move to the discrete version. Yeah. In application, a function is given by a sequence of equally spaced sampled data points. Yeah. Yeah. The sum file, yeah. How to get those numbers? Yeah. So, you know, you do the equally spaced sampling. You get sampling values equally spaced. For image file, also equally spaced sampling values. Okay, yeah, yeah. But here, this is you know, of the main cases. Yeah. But some signals, sometimes some other signals may not come from the equally spaced sampling. Yeah, because it's very hard to do the equally spaced sampling. Sometimes, in that case, still we do the sampling. Yeah, so we get sampling values, but the space between two adjacent signals, two adjacent sampling values, not equally spaced. Yeah, they are not equally spaced. That's another case. Yeah, but this one, for sound, for image, for videos, all fall into this category. Yeah, so let's study it. Because this case much simpler. Yeah, much simpler. So we study in this class. We studied this case. Yeah, equally spaced sampling values. Yeah. All right. Then, how to represent our data points. Yeah. X, Y coordinates. Each data point, X coordinate, Y coordinate. Okay. Yeah. The function value, F function value. But you get a sequence of those values. You will not give a nice function, nice formula. You never get a function represented with nice formulas. So you get a sequence of data points. You need to do processing. Okay, all right, and we assume 2 pi periodic. Okay, 2 pi periodic. As our base case. Because later when we study the signal, because typically the signal domain of the signal, not a 2 pi interval, okay? So the domain of the signal spread in the finite interval, AB. Lower bound A, upper bound B. There is a lower bound, there is an upper bound. Okay? For example, for the sound file, the lowest number, there is the smallest number, right? In your sound file. There is the largest number in your sound file. Okay? So you define a and a B. All the other numbers, between. It's not. That's the values. But the lower bound, because lower bound, higher bound for time domain, right? So here, we need to use the time domain. When you start, your sound file, there is a starting point, right? That starting point is the A. There is an end point, right? That is the B. So that number value, that's the, different thing. That's for the F function. Here we are talking about X coordinates. X coordinate between A and B. Then the higher, lower value, that's for the function values. For image, we also have that. Image, you have some. The domain, it's a 2D domain, right? The image, the 2D domain. So if you look at, the starting point, the area that you work, that area. So then the value, pixel value, high, low, But you also get a sequence of data. How do you get a sequence data? Row by row. The first row sequence of data, second row sequence of data, third row sequence of data, and so on. Okay? Or in a matrix. So typically what you get is, 2D array. What do you get? 2D array. Yeah. Yeah. You know. Yeah. Yeah. In that, yeah. Row by row. Yeah. So what do you see? The first row, the second row. Yeah. So each point, you have a location, then you have a pixel value, right? The location, pixel value. Yeah. So for the color images, you have RGB, 3 numbers to represent the pixel value. RGB values. Okay? That's for image. Yeah. For the video, then you have a sequence of images, right? Yeah. So the frames, right? So the videos, because we put a lot of frames in a video file. Okay? Each frame is one image, right? Each frame is a one image. See? Yeah. Yeah. All the signal, yeah, these 3 types, all equally spaced, sampled data points. So you can see, we target, so we are targeting this type of data, a lot of applications in the real world. Yeah. Yeah. All right. So then, representation, XK. XK, yeah. So we define, yeah. So this time, yeah, we look, XK represent the locations, right? Yes, here. Yeah. X-axis, okay? X-axis. Yeah. We do equally spaced sampling. Okay? Yeah. X1, X2, X3, and so on. Okay? Yeah. XK. Yeah. Yeah. So that XK, 2 pi times K over N. Yeah. Big N. That N, total number of points in the domain, yeah, in your AB interval. How many points? How many samples? So here we call samples. Yeah, the number of data points. Number of samples. Yeah. That's the XK notation. All right? Yeah. All right. Then question. How to approximate the function f of x with a convenient function? Yeah, because here, this f function is an imaginary function. Yeah. Because we are never given such a function, f function. Yeah. We are given a sequence of numbers, sequence of data points. Okay? But in order to apply our mathematical tools, we like to have a function to work on, right? If data points, how do we apply our mathematical tools on those data points, right? It's hard. It's hard to apply our mathematical tools. Yeah. So that we need to choose appropriate function to represent the data. Yeah. So that function, so here we can call, the modeling function. Modeling function. So here we want to choose a modeling function. Modeling function. Okay, modeling function. Yeah. Yeah. Convenient. With a convenient user. The function, nice function, yeah, with good properties. Yeah. So when we take derivatives, integrals, yeah, so we can do easily. Yeah. So convenient function. Okay? Yeah. All right. Use a complex trigonometric polynomial. So here, then people choose, so what special function you want to use? We use complex trigonometric polynomials. Yeah, not a real, okay? Complex, yeah. Yeah. And the people feel, if you use complex, then you can represent more real-world phenomena. Yeah, more real-world phenomena. Yeah, yeah, yeah. Because for the electricity signals, okay, yeah, electricity signals, yeah, people need to use the complex values. Yeah, so sometimes, yeah, some people need to use the complex values. All right, yeah. So then, the complex trigonometric polynomial, that's a nice modeling function. All right, but how to use complex function to represent here? What's the complex trigonometric polynomial? This format. Okay, yeah. The coefficients, C coefficients, they're the basis functions. Yeah, because when you represent this function, you need to use a set of basis functions. Yeah. So this e to the I and x. So these functions we use as the basis function. Yeah. And polynomial, yeah, because each term looks like a monomial, right? Yeah. Yeah. Polynomial, yeah, because each one, each e function, it's a e to the ix raised to nth power. Okay, raised to n. Yeah, that's we can treat as a monomial, right? Yeah, it's a monomial. Yeah. So then, yeah, we add up all these terms, we get a polynomial. Yeah. So this polynomial, it's a complex trigonometric polynomial. Yeah. Yeah. Because later for the e function we have sine and cosine in this e function. Yeah. So trigonometric, yeah, polynomial. The sine part and the cosine part. Because later, when we need to calculate the real part, yeah, for this complex function, we should have the real part and the complex part. The real part is the cosine part. The imaginary part, that's the sine part. All right, let's take a 10-minute break. So then when we come back, we need to look at the definition of the discrete Fourier transform. Yeah. In the first half, I give you the background. Yeah. Otherwise, what we are doing here, right? If you do not have enough background, so you couldn't understand why we do this kind of thing. Yeah. All right, take a break. Yeah.